Okay, what are your questions? Besides, you'd like to see a few more of those. Finding derivatives by definition. So let us start there. Remembering what we're looking at is given a function f of x. We define its derivative f prime of x to be the limit as h approaches 0 of f of x plus h minus f of x over h. And doing something like a polynomial, f of x equals, let's say 3x squared minus 2x plus 5, and prime of x would equal limit as h approaches 0, 3 times x plus h squared minus 2 times x plus h plus 5. Subtract 3x squared minus 2x plus 5 all over h. Doing the algebra in the numerator, limit as h approaches 0, 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 5 minus 3x squared plus 2x minus 5. All divided by h. And in the numerator, 3x squared adds out with its opposite, negative 3x squared. Negative 2x adds out with its opposite, positive 2x. And positive 5 adds out with its opposite, negative 5. Leaving limit as h approaches 0 of h times 6x plus 3h minus 2 all over h. Everywhere the h is not 0, h divides h. And that limit, the number over itself, the limit is 1. And now, since we no longer have division by a potential 0 value, we can allow the other h's to go to 0. 2 times 0 is 0, and we get 6x minus 2. Now, something to notice, of course, is that this is a function, but this is also a function. The derivative of a function is a function. In the case of a polynomial, each time you take the derivative, it reduces 1 degree. So if I take the derivative twice more, the second derivative, double prime, of x is, well, simply 6. And the third derivative of x is nothing. And in general, if we have an nth degree polynomial, our nth plus 1 derivative will be 0. Each time it steps down a degree, finally down to 0 degree. And if we're taking more than 3 derivatives, then we start using Roman numerals to indicate that we're taking 4th, 5th, 6th derivatives if they exist. Okay? Some functions, they do exist. Okay? Well, let's take another one. Well, let's work some of the problems in. I want to say in 3.1. Not 3.1. Let's go to 3.2. And some of the problems there, just to give us 1 or 2 to get started. Number 4. K of z equals 1 minus z over 2z. 2z. And in particular, once we find the derivative, we want to find k prime when z is 1. We'll find k prime when z is, what's next up? Oh, first one was negative 1, positive 1, and square root of 2. So, since we don't have any rules for this yet, we just have the definition. We apply the definition. K prime of z is equal to the limit as h approaches 0 of 1 minus paren z plus h over 2 times z plus h minus paren 1 minus z over 2z, all that divided by h. And again, we have a compound fraction, so we want to simplify the fraction. Multiply through by the lowest common denominators over itself, which is 2 times z plus h times z over 2 times z plus h times z. Now make the compound fraction into a simple fraction. In the numerator, multiplying this times this, 2 divides, and the z plus h divides, so all I have is limit as h approaches 0 of z times this, which is z minus z times z plus h. Subtract this times this. The 2z divides out, leaving z plus h as a multiplier. So I have 1 minus z times z plus h. And my denominator is h times 2 times z plus h times z. Now when I do the arithmetic or the algebra in the numerator, it should simplify some. Equals limit as h approaches 0 of z minus z squared minus zh, 1 times z minus z, 1 times h minus h, z times z plus z squared, z times h plus zh. All over my h times 2 times z plus h times z. In the numerator, plus z adds out with its opposite, minus z. Minus z squared adds out with this opposite, z squared. And let's see, this is minus zh plus zh. So they add out, leaving limit as h approaches 0 of minus h over h times 2 times z plus h times z close. And now the h's divide, leaving -1 in the numerator. And we can let h go to 0 down here. So we end with -1 over 2 times z times z. What is that term? That 2z squared. Now, Another way to have looked at this problem, 1 minus z over 2z, if we write it as two fractions, we have 1 over 2z minus 1/2. And if you remember, one of the ones we did last time was 1 over x. And when we did 1 over x, its derivative was minus 1 over x squared. So think of this as 1/2 times 1 over z. And what we get here is minus 1/2 over z squared, which we have. And turns out the derivative of a constant, it's never changing, so its slope is 0, so to speak. So its derivative is 0. So the derivative of this messy looking thing is really just the derivative of that part of it. And that would have been easier algebraically, but you don't always see that easier step necessarily. So it would be nice if we didn't have to do this painful process. Let's do one more just for good practice. F x equals x to the 6th. F prime of x equals the limit as h approaches 0 of x plus h to the 6th minus x to the 6th over h, which is the limit as h approaches 0 of x to the 6th plus 6x to the 5th h plus 15x cubed, x to the 4th h squared plus 20x cubed h cubed plus 15x squared h to the 4th plus 6x h to the 5th plus h to the 6th. That's that term. Minus x to the 6th all over h. Add out like term. X to the 6th adds out with its opposite. Factor in h. Limit as h approaches 0 of h times 6x to the 5th plus 15x to the 4th h plus 20x cubed h squared plus 15x squared h cubed plus 6x h to the 4th plus h to the 5th all over h. That h divides. So now, since I no longer have division by 0, I can allow h to go to 0, which makes this term 0, 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 and we're left with 6x to the 5th. Okay. And we kind of saw that pattern last time when we were dealing with powers of x. But it'd be nice to know if it's true for all powers. So we're going to go back to the definition and build a set of rules which allow us not to have to do this every time. But unfortunately, rules don't just magically appear from hyperspace and show up on board. We have to demonstrate that those rules are correct. And the only tool of demonstration that we have is that definition. So, let's erase some of this and jump in. So, if f of x equals a constant, then f prime of x, by definition, is the limit as h approaches 0 of, what is f of x at x plus h? Well, it's a constant, so it's c, subtract f of x, c over h. This is 0 everywhere when h is not 0. If we graph this as a function, it would be the x-axis with the exception of that point. So having said that, where does it look like it's going? And the answer is, it's going to 0. So there's our first form. So if I said f of x equals 73,892,468.4195, f prime of x is that's a horizontal line at 73 million and change above the axis. It has no slope, it has a slope of 0. Okay, so that's easy enough. So let's go to the next one. A constant times a function. Given the function f, or c times f of x, we'll find its derivative. Definition says this is the limit as h approaches 0 of c times f of x plus h minus c times f of x over h. C is a common factor, so this is the limit as h approaches 0 of c times f of x plus h minus f of x over h. So we have a product here of a constant times a function. Well, when we're looking at the rules for limits, the limit of a product is the product of the limits. So technically this is the limit as h approaches 0 of c times the limit as h approaches 0 of f of x plus h minus f of x over h. Well, the limit of c, no matter what h is, c is constant, it doesn't change. So this is c, and this is the definition of the limit. I mean, the definition of the derivative f prime of x. So let's begin writing some of these over here. Let's talk about here. F of x, f prime of x. Constant, 0. Constant times the function gives a constant times derivative of the function. So let's continue in this arithmetic vein and look at sum of two functions, f of x plus g of x prime, that derivative. By definition, limit as h approaches 0 of f of x plus h plus g of x plus h minus f g of x all over h, which regroup terms limit as h approaches 0, f of x plus h minus f of x plus g of x plus h minus g of x over h. Right, this is two fractions. Like, 8/9 can be written as 1/9 plus 7/9. Separated fraction. So this is limit as h approaches 0 of f of x plus h minus f of x over denominator h plus g of x plus h minus g of x over the denominator h. And the limit of a sum is the sum of the limits when the limits are nice. So this is the limit as h approaches 0, f of x plus h minus f of x over h, plus limit as h approaches 0 of g of x plus h minus g of x over h. And this first limit is precisely the definition of f prime. And the second limit is precisely the definition of g prime. So now we have the derivative of a sum, f of x plus g of x, is equal to the sum of the derivatives, f prime of x plus g prime of x. Okay. Well, the difference is about as easy. F of x minus g of x, prime, limit as h approaches 0, f of x plus h minus g of x plus h minus f of x minus g of x over h. Again, recombining terms, limit h approaches 0, f of x plus h minus f of x minus g of x plus h plus g of x over h. As we did over there, let's write it as two fractions equals limit as h approaches 0 of f of x plus h minus f of x over h. Factor -1 out of this and it becomes -1 times plus minus g of x plus h minus g of x over h. And just as the limit of the sum is the sum of the limits, the limit of the difference is the difference of limits. This is limit as h approaches 0, f of x plus h minus f of x over h. Subtract the limit as h approaches 0, g of x plus h minus g of x over h. And this is precisely f prime of x, subtract, and this is precisely g prime of x. So we have a difference rule. F prime of x, f of x minus g of x. The derivative is f prime of x minus g prime of x. Now, it'd be real nice if the derivative of a product is the product of the derivatives. But unfortunately, that's not the way it's going to turn out. It's a little more complex than that. But that's why we have our definition to work through. F of x times g of x is the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x over h. Well, algebraically, as it is, there's not much I can do with it. But you're familiar with multiplying by 1. In other words, 4/6, we multiply it by 1/2 over 1/2 becomes 2/3. So we commonly multiply by a well-chosen 1. One is rationalizing numerators as multiplying by the algebraic conjugate over the algebraic conjugate, multiplying by 1. Here, instead of multiplying by 1, we're going to add 0. And 0 can be expressed in a variety of forms. Like 0 is 3 plus -3. Or 11/6 minus 11/6, still 0. So the 0 I'm going to choose to add, limit as h approaches 0, f of x plus h times g of x plus h minus f of x times g of x plus h plus f of x times g of x plus h minus f of x g of x. And these two terms I tossed in here add up to 0. So adding 0 to something doesn't change anything. Let's not forget. Divided by h. So now let's regroup limit as h approaches 0 and also do some factoring. In these first two terms, g of x plus h is a common factor. So I'll write this as f of x plus h minus f of x over h times g of x plus h plus f of x times g of x plus h minus g of x over h. And once again, as before, the limit of the sum is the sum of the limit of the product of the limits. So we can take all these limits. Limit. Let's take the limits. This is f of x. F prime of x, I should say. This is, as h goes to 0, this is just g of x. Plus, this is f of x. And this is, as h goes to 0, is g prime. So, we see a product, f of x times g of x. The derivative is f prime of x times g of x plus f of x times g prime of x. That is derivative of the first times the second plus the first times the derivative of the second. And if we had several functions, p of x, q of x, r of x, that derivative would end up to be p prime of x, q of x, r of x, plus P of x, Q prime of x, R of x, plus P of x, Q of x, R prime of x. So if we have more than a pair of factors, the derivative just steps its way through. Derivative of the first, derivative of the second, derivative of the third, and it would step on down if we needed to do that. Now that's a good little exercise to demonstrate it, at least for the multiple of three things. So, let's look at a quotient. First thing to notice on a quotient is what's true with any quotient. The divisor cannot be zero. So if I have Q, how about f of x over g of x, stick to the notation we've been using. F of x over g of x, with the note that g of x cannot be zero. Derivative of that. Limit as h approaches 0 of f of x plus h over g of x plus h minus f of x over g of x over h. Again, compound fraction. So we choose to multiply by a well-chosen 1, g of x plus h times g of x over g of x plus h times g of x. And when we do that, limit as h approaches 0. This first term, the g of x plus h goes away. We have f of x plus h times g of x. In the second term, the g of x goes away, and we have minus f of x, g of x plus h. And the denominator now becomes h times g of x plus h times g of x. And as I did with the multiplication, I'm going to add 0. I think you want to pick a nice 0. So this is a limit as h approaches 0 of f of x plus h times g of x minus f of x, g of x plus f of x, g of x minus f of x, g of x plus h, all over h times g of x plus h times g of x. Okay. Again, grouping this stuff, limit as h approaches 0 of common factor g of x, f of x plus h minus f of x over h times g of x over g of x plus h times g of x minus f of x is a common factor, f of x times g of x plus h minus g of x over h over g of x plus h, g of x. Okay. This first term, f prime of x. This term, as h goes to 0, we have g of x over g of x times g of x. So one of those could divide out. But I want the same denominator here, so I'm not going to do that division. G of x minus f of x times this mass, which is g prime of x, and both of these are over the denominator g of x squared. Because if that h goes to 0, we have g of x times g of x. So in the case of a quotient, f of x and g of x, note g of x cannot be 0. The derivative is derivative of the numerator times denominator, subtract numerator times derivative of denominator over the square of the denominator. Okay? So then we have 1, 2, 3, 4, 5, 6 rules so far. So it just applies to any and all functions. So, you know, we have function types. We have polynomials, we have rational functions, we have exponential functions, we have logarithmic functions, we have trigonometric functions, we have hyperbolic trigonometric functions, or hyperbolic functions. So there's a whole family of functions that we need to start looking at. And of that list, the easiest one to look at is polynomials. But because of our constant times a function, sum of functions, difference of functions, every polynomial is a constant times a power of x, plus another constant times another power of x, plus another constant times another power of x. But we only have to worry about one at a time. So let's just worry about x to the n. Now, one reason I did the x to the 6th earlier is so that you kind of see what those terms are in the expansion of x to the n. This is the limit as h approaches 0 of x plus h to the n minus x to the n over h. Well, the binomial theorem tells me this, that a binomial raised to a positive integer power, a to the n plus n times a to the n minus 1 times b plus n times n minus 1 over 2 times a to the n minus 2 b squared plus n times n minus 1 times n minus 2 over 6 times a to the n minus 3 b cubed plus and so on, till finally we get the last term, which is b to the n. These denominators are really 0 factorial, 1 factorial, 2 factorial, 3 factorial, all the way to n factorial. Okay. This one divides out because the coefficient here is also n factorial. Okay. So expanding this using that form, limit as h approaches 0 of x to the n plus n times x to the n minus 1 plus times h plus n times n minus 1 divided by 2 times x to the n minus 2 h squared plus n times n minus 1 times n minus 2 x to the n minus 3 h cubed over 3 times 2 times 1, 2 times 1 times 1, 1 plus, I'll skip a few, general term will be where this symbol is on your calculators NCR, and it is n factorial divided by n minus r factorial r factorial. That's what all these become. That's what these are. And if n is not too large, each term below is equal to the sum of two terms above. 10 plus 10 is 20. 10 plus 5 is 15. And if we go back to the one that we did, x to the 6th, the coefficients of that expansion were, or the whole thing was, x to the 6th plus 6 x to the 5th h plus 15 x to the 4th h squared plus 20 x cubed h cubed plus 15 x squared h to the 4th plus 6 times x h to the 5th plus h to the 6th. Those are the coefficients, which are generated using combinations based upon the binomial theorem. Okay. Plus, skip a few more. Last term is h to the n. No, I missed something. No. Okay. Let's do the last two terms. N times x to the first h to the n minus 1 plus h to the n minus x to the n all over h. And once again, we see that x to the n adds out with this opposite, the opposite of x to the n. And there's a common factor of h in every other term. H to the first, h to the second, h to the third, h to the r, h to the n minus 1, h to the n. They're all in there. Write that in factored form. Limit as h approaches 0 of h times n times x to the n minus 1 plus n times n minus 1 over 2 times x to the n minus 2 times h plus n times n minus 1 times n minus 2 over 6 times x to the n minus 3 h h squared plus and so on plus h to the n close, or h to the n minus 1 close over h divides now we let h become 0 and every term with an h in it. And the only non-zero term that's left so looking at that, the old exponent becomes a coefficient. A new exponent is one less than the old exponent. This is a lot easier than doing it that way. So, continuing our list, f of x, f prime of x, x to the n becomes n times x to the n minus 1, for n a positive integer, or a natural number if you wish. Okay, so with these tools that we have so far, we can find the derivative of any polynomial. So let's find this one using these rules. P prime of x is (407) x to the 10th. I did the hard one. What's this one? 119 x to the 6. The next one?
24x to the 2nd.
And the next one?
5.
And the next one?
0.
Piece of cake. Why did we bother to do all that work last time and at the beginning of the period this time? The answer is very simple. Talked about some last time. What is the answer? How do you get the answer? And why is the answer what it is? Well, these are the hows. How do you get the answer? Well, why the answer is what it is by following through on the definition of the derivative. Now, having said that, on the test, there may be a couple of problems that say, find the derivative of the following function or functions by definition. So if I gave you this and said, do this by definition, you'd be busy the rest of the week. Because that expanded will give me 12 terms. That would give me 8 terms. That would give me 4 terms. How many are we up to? 8, 12, 4, 24. That would give me 2 terms. 26. Fortunately, that wouldn't give me any more terms. Yeah, it would. 1 more term. 27. plus these again, 28, 29, 30, 31, 32 terms in the numerator. Bummer to do that manually. But we have this nice little set of rules. Derivative of the constant, 0. Derivative of the constant times the function is the constant times the derivative of the function. Derivative of a sum, do I have a sum in here? Derivative of sum, the sum of derivatives. Derivative of difference, the difference of derivatives. Piece of cake. And we can do products. Now, here you actually have an option. You can multiply all that out first. Then we'd be dealing with a 4th degree polynomial rather than 2 2nd degree polynomials. I'm going to use a product rule because we have it. So the derivative is, got time to retire this one. Heads up in the back. Wastebasket is close to you. Out of swing room, I'm sorry. We'll try the next one. Okay. Derivative of the first, 6x plus 5, times the second, 7x squared minus 2x plus 13, plus the first, 3x squared plus 5x minus 4, times derivative of the second, 14x minus 2. And we can do quotients. If I have r of x equals, let's not make it too hard, 3x plus 2 divided by 5x minus 4. Then r prime. R standing for a rational function. Polynomial divided by polynomial. The quotient rule says derivative of the numerator times denominator, subtract numerator times derivative of denominator over square of the denominator. Now this one, the numerator simplifies. 15x minus 15x goes away. Negative 12 minus 10, negative 24, over 5x minus 4. Piece of cake. But one of the ones we did last time, well, we did a couple that did not fit this pattern. Oh, that was not a grenade down the hall. Okay. What if we have f of x equals x to the minus n? We really have this covered because this can be written as 1 over x to the n. And then it's a quotient. A constant function divided by a non-constant function, but still a ratio of functions. So we can use the quotient rule f prime of x is derivative of the first times the second, or derivative of numerator times the denominator minus numerator times derivative of the denominator all over the square of the denominator. If we simplify this, this goes away. I have minus n over, now I want to combine these two. So let's see, 2n subtract n minus 1 is n plus 1. Oh. X to the n plus 1, which is equal to minus n times x to the minus n plus 1. And we did one of those yesterday. X to the minus 1, the derivative is minus 1 over x squared. So in fact, this rule for finding a polynomial derivative, that is, power rule, works for negative integers as well. Now let's look at another one we did. You might recall that we did the square root of x. And let's go and do this again. By definition, f prime of x is limit as h approaches 0 of the square root of x plus h minus square root of x over h multiplied by well-chosen 1, square root of x plus h plus square root of x over square root of x plus h plus square root of x close is x plus h limit as h approaches 0, x plus h minus x over h times square root x plus h plus square root of x close. The numerator, the x's add out, and we're left with limit as h approaches 0 of h over h times square root of x plus h plus square root of x close. The h's divide, leaving 1 over, this h goes to 0, square root of x plus square root of x, 1 over 2 times the square root of x. Okay. But if I write this thing in exponent form, not radical form, and apply the same rule says the derivative of that is the old exponent becomes the new coefficient, and the new exponent is 1 less than the old exponent. What's 1 less than 1/2? Negative 1/2, which we can write in the denominator as a positive 1/2. So this power rule applies to all rational numbers as well. But we want to go just a step further. And this is one of the arguments that separated Newton from Leibniz. I'm not going to prove, but at least I'll sketch it out. If n is not a positive integer, then x to the n, when you start doing the process, expanding it, x plus h to the n, never ends using the expanded or generalized binomial theorem. That is, if f of x equals x to the r, where r is any real number, then f prime of x, limit as h approaches 0 of x to the r plus h minus x to the r over h. Quite frankly, that doesn't simplify very nicely. Oh, I'm sorry, I knew I did that wrong. X plus h to the r. Okay. This thing starts out as it did before. X to the r plus r times x to the r minus 1 times h plus r times r minus 1 times x to the r minus 2 h squared plus r times r minus 1 times r minus 2 times x to the r minus 3 h cubed. And these have denominators: 0 factorial, 1 factorial, 2 factorial, 3 factorial, plus and so on. The thing is, even though the powers of h are nice positive integers, the powers of r are not. For instance, if I take r to the 1/2, then we have 1/2, negative 1/2. 1/2 times negative 1/2 is negative 1/4 times to the negative 3/2. The next one is negative 5/2. The next one is negative 7/2. It never goes away. This goes on forever. Minus x to the r over h. Just as before, the first term adds out with the last term. Every other term has powers of h. If I divide by h, this term is the only term left that will not have an h in it. And the all other terms will have h's in them. And no matter what power of x we're dealing with, the magnitude of these terms in the limit is 0. So if I have, I don't know, x to the pi, the derivative is pi times x to the pi minus 1. So finding derivatives of powers of x is no problem. They all follow the power rule for n a positive integer, as well as the power rule in general where r is any real number. Isn't that nice? Okay. Well, there's one more rule I want to develop, and then we're going to practice applying these rules. And And that is, you're not going to have to repeat this, you know. I mean, I just kind of sketched this. I did not really prove it. Just take my word that all adds up to 0. But Newton was able to prove that, and Leibniz was not. One reason the eventual prize went to Newton, not to Leibniz. Okay. Although, like I say, we use Leibniz's notation as much or more than we use Newton's notation. Okay. There's a function out there that's kind of interesting. It's a function that says one point on it is 0, 1. And for every point on the function, the slope of the function at that point is equal to the y value. So whatever this curve does, as it comes through 0, 1, it has a slope of 1. Which seems to mean that the value of y is increasing. So the slope is increasing on this side. As we go this way, the slope of the function is decreasing. So this function looks something like this. It's asymptotic to the negative x-axis, goes through 0, 1, and climbs equal like that. And we can give this function a name. This function's name is e to the x. Okay. Now I just told you that we define it so that the slope of the function is equal to the value of the function. That is, I'm saying that the derivative of e to the x is e to the x. But let's approach that differently. Let's do it empirically. If I have e to the x, I want to know its derivative. Limit as h approaches 0, e to the x plus h minus e to the x over h. Using our rules of exponents, this can be written as e to the x times e to the h minus e to the x over h. I factor e to the x, limit as h goes to 0 of e to the x times e to the h minus 1 over h. This has no h's in it, so it can come out. E to the x times the limit as h approaches 0 of e to the h minus 1 over h. It would be very nice if that limit is 1. Now, I said I'm not going to prove that, but we're going to do it empirically. That means we're going to throw in a lot of values of h, very close to 0, because that's what we're asking. What's the limit of this when h approaches 0? So to be fair, let's look at h and e to the h minus 1 over h for different values. Let's start with 0.01 and negative 0.01 and 0.0001 and negative 0.0001 and 0.00001 and negative 0.00001. I'll do the positive side first. My handy dandy TI-89 calculator. I'll show someone up close my results. Let's clear all this. Clear, 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 clear. Clear. Okay. How good are your eyes reading close? It says paren e to the x minus 1 or minus 0.1, whatever it says. It says e to the 0.01 minus 1 over 0.01. It's this one. Enter, and it says 1.0050, 1.00501667 and on. Let's go this one. Add a couple of zeros to that. 0, 0, 0, 0, and it says 1 point 0, 0, 0, 0, 5, 0, 0, 0, 0, 5, 0, 0, 0, 2. Let's go down to that one. 5 zeros. Okay. 0, 0. Five zeros. Enter. And my calculator says 1 point 1, 2, 3, 4, 5, 0, 0, 0, 0, 0, 0, 5. And just save time and expense, I'll just look at this one on the negative side. So, change that sign to a negative. Change that sign to a negative. Enter. And my calculator says 1, 2, 3, 0.99999995. So what do you think this limit is? Very darn close to 1 to me, isn't it? So, remember e to the x is e to the x. And the derivative of the derivative of the derivative of e to the x is e to the x. Stays e to the x no matter how many derivatives you take. Kind of a nice function. Only easier function than that is 0. Derivative of 0 is 0. And that goes on all the way. Okay. Well, that was kind of nice. Let's look at one just a little different. Let's look at 7 to the x. Derivative. Limit h equals 0. 7 to the x plus h minus 7 to the x over h, which is the limit h approaches 0. Factors again, 7 to the x times 7 to the h minus 1 over h, close. This is equal to 7 to the x times the limit as h approaches 0 of 7 to the h minus 1 over h. Well, if that derivative was 1, what do you think this derivative is? It'd be not derivative. If that limit is 1, what do you think this limit is? It'd be nice if it's 1. So I think I'm going to replace the e on my calculator with 7 and throw this one in with, instead of e to the x, have 7 to the x. So let's do that. So I want 5 zeros and a 1, 5 zeros and a 1. I want to change my e to a 7. So now I have 7 to the x minus 1 over x. This is what I have in the calculator. Push my button, and it says, doesn't say 1. Bummer. It says 1.945912. What is that number? Maybe I have a TI-84 in front of them.
have a, trying to do it on TI now. What is the natural logarithm of 7? What does your calculator show the natural log of 7 to be? That is, let's see, second, which is the blue key. And then a couple of 3 lines below that is the X key. But when we do second, it gives us natural log. And then we enter 7. And then you hit enter. However, somebody do that, what does this show when you do that? I think it shows natural log 7. So, do the diamond key and enter. And it shows 1.94591014906 and change. So what do you think this limit is? Natural log of 7. So I'm going to add one more to the list where I have an exponential other than e to the x. The derivative is b to the x, natural log of b. So let's turn to the problems in section 3.3. And attack a few of those. And I'm going to begin with number 4. And you notice it says find the first and second derivatives. Okay. First and second derivatives. Let me erase a whole bunch here. Years ago at the University of Oklahoma, I was teaching a trig section with 200 students in it. I was using 2 overhead projectors. One overhead projector, I had my prepared notes on there and, trig stuff. The other overhead projector is the one I'd work problems out on. So I'm in class one day, and about 5 minutes into the class, bulb goes down on that overhead projector. So now it's show the prepared slide, work problem, show the prepared slide, work problem. About 5 minutes later, second projector went down. So I have a room full of 200 students who think, man, we're out of here. And I went over the wall and pushed the button, and the screens go up. And there's a 4-panel chalkboard behind me. You could hear them go, oh. But in college courses, you can't afford to get behind so much. So, anyway, number 4. And we'll do this until my voice is totally gone and we all pass out from exhaustion. 3z to the 7th minus 7z to the 3rd plus 21z squared. W is 3z to the 7th minus 7z to the 3rd plus 21z z squared. Is that what it say? Yeah. So, W prime is, help me out here, first term. Z to the 6. 7 times 3 is 21. 1 less than 7 is 6. Second term.
21z to the second.
21z to the second. Third term. The second derivative.
Z to the fifth.
126z to the fifth minus 42z plus 42. And why don't we find some more? I. Prime. 5 times 126. 630. Z to the fourth minus 42. WIV. 240, 245. That's 24, or 25, 20. Z cubed. W5 is 75, 60. Z squared. VI 6 power is 15, 16, 16, 20, 16, 200, 162, Z, W7, VII is 16200, W8, VII is 0. That just demonstrates that an nth degree polynomial, the n plus first derivative is 0. Okay, number 10. Y equals 4 minus 2x minus x to the negative 3. Y equals 4 minus 2x minus x to the negative 3. Y prime is nothing. Negative 2. Negative 3 times negative 1 is positive 3. 1 less than negative 3 is negative 4. And they ask for two derivatives. Negative 12x to negative 5. Okay. Number, let's go to 18. E equals 4 minus 3x. Divided by 3x squared plus x. So z prime, this is the quotient. Derivative of the numerator, negative 3 times denominator, 3x squared plus x, minus numerator, 4 minus 3x, times derivative of denominator, 6x plus 1. All of that nicely divided by 3x squared plus x, all squared. Let's go down to number 26. R equals 2. R equals 2 times 1 over root theta, because it's a plus root theta. writing it in exponential form rather than radical form, r equals twice theta to the minus 1/2 plus twice theta to the 1/2. R is equal to minus 1/2 times 2 is minus 1 over 1 less than negative 1/2, 1 less than negative 1/2. Negative 3/2. 1/2 times 2 is 1. Theta is negative 1/2. So I have a solution. Theta to negative 3/2 plus, theta, that's minus theta to negative 3/2 plus theta to the minus 1/2. Now, that is correct. However, what form was the problem given in? If the problem is given in radical form, we should be consistent with the presentation of the problem, so we should give this in radical form. This is theta to the 3/2. That's theta to the 1/2. Let's look at theta at number 34. X to the negative 3/5 plus pi to the 3/2. X to the negative 3/5 plus pi to the 1/2. And what was this? What kind of 34? White. Be careful here on this one. Y prime is negative 3/5 x to the, what's 1 less than negative 3/5? Come on, arithmetic of fractions. Negative 8/5. And what's this one? No. Do you see any variables here? There's no variables here. What's the derivative of a constant? 0. So I'm done. This is it. Because that one goes to 0. Derivative of a constant. Square root of pi, I don't know what it is, but its derivative is 0. Okay, number 42. Find the derivative of all orders of the function in exercise 41 through 44. And this is pretty easy. Y equals x to the 5th over 120. Y prime x to the 4th over 5 times what is 120? Y double prime is x cubed over 8. Y triple prime is x, about 3x squared over 8. Y IV is 6x to the 1st over 8. Oh, that reduces 3/4. And the last one, y to the 5th, oh, not yet, 3/4. And y to the 6th, or derivative of the 6th power is 0. If I did everything correctly. Okay. An interesting problem is number 64. And here's the setup. I don't think I'm going to work it. but we have a parabola and a point not on the parabola. Now, if that point's on the interior, there's no solution. If that point is on the exterior, as this one is, then there are two solutions. Because it's asking for the slope of the tangent line to the curve through the given point. There'll be one down here somewhere, but there'll also be one up there somewhere. So, this curve was simply y equals x squared, and the point was what, 3/8? Okay. Well, what's the derivative of this? Y prime, that is, the slope, is 2 times x. And this is some point xy, or x squared. What's the equation of a line through 2 points? Equation of a line through 2 points is the difference in the y values over the difference in the x values, and this must equal the slope of the curve at that point So now we have a quadratic equation in x multiplied by x minus 3. We have x squared minus 8 is equal to 2x squared minus 6x. Bring everything to this side. 0 equals 2x squared minus 6x plus 8 divided by 2. 0 equals x squared minus 3x plus 4. That factors. No, it doesn't. But we can throw in the quadratic formula. I did my arithmetic right. Did I do my arithmetic right? No, I didn't. Just threw that one. I did messed up my algebra. My goodness. Okay. I am right to this point. Again, x squared minus 8 is equal to 2x squared minus 6x. Bring this to this side and it becomes x squared minus 6x plus 8 equals 0. And now, that doesn't factor, but x is equal to minus b plus or minus square root b squared minus 4 times a times c. Oh, it does factor. What am I thinking? 32 over 2. This factors. X minus 4 times x minus 2. So x equals 4 or x equals 2. And the slope is 2x. And what did it ask? It asked for the slope. What did it ask for? Find the points. Okay. So if x is 2, x squared is 4, and if x is 4, x squared is 16. So we have the point 24 somewhere, and point 416 somewhere. Are the 2 points solved?
What was that?
That was number 64.